Manchester, November 1873, 3 o'clock in the morning. The night shift at Ashworth Mill heard it first. Not a bang, not a crack, something quieter, something that didn't belong. A whisper. Thomas Drayton, a boiler tender with 11 years' experience, described it in his testimony as a voice trapped in iron. Others called it singing, ringing. One man swore the boiler was alive. The sound wasn't constant. It came in waves, a soft metallic tone that rose and fell with the pressure cycles. Sometimes it lasted 30 seconds, sometimes 3 minutes, always between midnight and dawn when the mill ran quieter and you could hear what the machinery was really doing. Picture the scene. A vast brick hall, 40 feet high, lit by gas lamps that turned the steam into golden clouds. The air tasted of coal smoke and hot metal. Your shirt stuck to your back even in November. The main boiler sat in the center like a sleeping giant, 12 feet long, 5 feet across, wrapped in riveted iron plates that had been hammered together by hand. And from somewhere, deep inside that iron shell, the whispering. Workers started gathering around it during breaks, standing close, pressing their ears to the warm metal. Some claimed they could hear patterns in it, rhythms that repeated, tones that shifted. One spinner said it reminded him of wind through a flue. Another said it was like hearing someone hum on the other side of a locked door. The foreman, William Garrett, told them to get back to work. Told them it was just steam finding its way through the pipes. Told them a boiler that size made all kinds of noises and they'd never noticed before because they'd never stopped to listen. But Thomas Drayton had been listening to boilers for over a decade, and he knew this wasn't normal. He started a logbook. Every time he heard the sound, he wrote it down, the time, the pressure reading, the temperature, how long it lasted. He noticed something. The whispers were getting louder, and they were happening more often. By the third week of November, the sound had changed. It wasn't just a hum anymore. There was a resonance to it, a vibration you could feel in your chest when you stood close enough, like standing near a church bell after it's been struck. Some of the younger workers refused to go near it. They said the boiler was trying to tell them something. Garrett called them superstitious and docked their pay. But on the night of November 28th, even Garrett stopped to listen. Because the boiler wasn't whispering anymore. It was breathing. The Ashworth boiler was what engineers called a Lancashire type. 2 parallel furnace tubes running the length of an iron shell, wrapped in water that turned to steam under pressure. Simple design, proven design, hundreds like it were running across England. But this one had a history. It had been built in 1869 by a contractor named Joseph Heap, who'd underbid every other ironworks in Manchester to win the contract. To save money, Heap used thinner steel plates than the original specifications called for, 1/4 inch instead of 3/8. The difference seems small until you understand what it means. 25% less metal, holding back 200 pounds of pressure per square inch. The riveting was uneven. Some seams had been hammered tight by skilled workers. Others had been rushed by apprentices working 12-hour shifts. You could see the difference if you looked close. Gaps where the plates didn't quite meet, rivet heads that sat crooked, places where the metal puckered instead of lying flat. And Garrett ran it hard. The mill operated around the clock, 3 shifts, no shutdowns except Christmas Day. To keep pace, Garrett overfired the furnaces, shoveling in more coal than the design allowed, pushing the pressure higher than the safety valve was rated for. He'd wired the valve partially closed so it wouldn't vent steam and waste fuel. By late 1873, the boiler was running at pressures it was never meant to handle, and it was starting to show. The first warning sign came in October. A door on the firebox began rattling during the night shift, not violently, just a persistent vibration that made the hinges click against the frame. Garrett stuffed rags around it and told Drayton to stop complaining. Then the pipes started sweating. Condensation appeared where it shouldn't, on the outside of steam lines, on the shell itself near the rivet seams, water beading up and dripping onto the brick floor. It meant the temperature differentials inside the boiler were extreme, hot spots and cold spots creating stress. Workers started reporting headaches, dizziness, a pressure behind the eyes that wouldn't go away. They blamed the coal smoke, the long hours, the heat, but Drayton suspected something else: low-frequency vibrations traveling through the factory floor and into their bodies. Vibrations too low to hear clearly, but strong enough to feel. By mid-November, the shell itself was moving. Not much, just a few thousandths of an inch, but enough that you could see it if you watched the gaslight reflections on the wet metal. A rhythmic flexing, in and out, like a lung. Drayton went to Garrett with his logbook, showed him the pattern, the increasing frequency of the sounds, the physical signs of stress. He didn't use the word whisper this time. He used the word failure. Garrett looked at the numbers, looked at Drayton, and said, "Shut it down and we lose 3 days of production. Cost us £200. You want to explain that to Ashworth?" Drayton didn't. He went back to his station and kept the logbook going. On November 26th, a small steam leak appeared at a rivet seam near the top of the shell, a thin jet of vapor that hissed when the pressure peaked. Garrett watched it for 10 minutes, then told a fitter to pack it with graphite paste and tighten the rivet. The leak stopped. The whispers got louder. Here's what was happening inside that iron shell, and why no one in 1873 could have fully understood it. When steam fills a pressure vessel, it doesn't sit still. It moves, it circulates. Hot steam rises, cooler steam sinks. The temperature differences create currents, convection patterns that flow through the boiler in invisible loops. Now add the furnace tubes, 2 long iron cylinders running parallel through the water, radiating intense heat from burning coal. The water nearest the tubes boils violently. The water farther away stays just below boiling. This creates pressure waves, pulses of expanding steam that travel through the water like ripples on a pond. Most of the time, these waves are random, chaotic. They cancel each other out. You don't hear them because they don't have a pattern. But the Ashworth boiler had something most boilers didn't: a geometric quirk. The distance between the 2 furnace tubes happened to match the wavelength of a specific frequency of pressure oscillation. When the steam pulses hit that frequency, around 47 cycles per second, they reinforced each other instead of cancelling out. This is called harmonic resonance, the same principle that makes a wine glass sing when you rub its rim, the same physics that can shake a bridge apart if soldiers march across it in step. The pressure waves began to synchronize, to amplify, and when they hit the thin steel plates of the boiler shell, they made those plates vibrate. But here's where it gets worse. The shell had microfractures, tiny cracks, some no wider than a human hair, running through the metal near the rivet holes. These fractures had been growing since the day the boiler was installed, spreading slowly through the steel every time it heated and cooled, every time the pressure spiked and dropped. Metal fatigue. We have a name for it now. In 1873, they just knew that old boilers sometimes exploded for no obvious reason. The microfractures acted like amplifiers. When the pressure waves made the shell vibrate, the cracks caught those vibrations and intensified them, turned a low hum into an audible tone. The sound traveled through the iron, through the rivets, through every piece of connected metal. And because the cracks were growing, the sound was changing, getting louder, shifting frequency, creating harmonics and overtones that sounded almost musical. To Thomas Drayton, standing 3 feet away with his ear near the warm shell, it sounded like whispering, like a voice just out of range. His brain, wired to find patterns, to hear language in noise, interpreted the resonance as something human. It wasn't. It was physics, pure and brutal. The boiler was tearing itself apart at the molecular level, 1 cycle at a time, and the sound was the machine's way of announcing what was coming. Every pulse was a warning, every tone was a countdown. The workers called it whispering because they didn't have the vocabulary to call it what it really was: the sound of impending catastrophic failure. November 29th, 1873. Second shift, 7 o'clock in the evening. Thomas Drayton arrived early. He'd barely slept. The headaches had gotten worse, and he'd spent the previous night lying in bed, feeling his bones vibrate with a frequency that shouldn't exist. When he entered the boiler room, he knew immediately something had changed. The sound was different, deeper. There was a low-end rumble now, below the metallic ringing. He put his hand on the shell and felt it thrumming against his palm like a living thing. The pressure gauge read 190 pounds per square inch, higher than it should be. Garrett had the furnaces roaring. Drayton found him near the coal pile, sleeves rolled up, face slick with sweat. "We need to shut it down," Drayton said. "No preamble, no logbook this time." Garrett didn't even look at him. 2 more hours, and we hit quota for the week. "Listen to it." "I am listening. It's working fine." "It's not." Garrett turned then, and Drayton saw something in his face, not anger but fear. Garrett knew. He'd been hearing it too, but admitting it meant admitting he'd ignored every warning sign for 2 months, meant losing his job, maybe worse. 2 hours, Garrett said again. Drayton walked back to his station. He didn't argue. What was the point? He'd file a report after the shift, document everything, let someone else make the call. He never got the chance. At 8:47 p.m., the vibration changed. Every worker on the floor felt it. A sudden shift in frequency, like when a train wheel hits a bad section of track and the whole car shudders. The boiler shell began to flex visibly now, the metal plates bowing outward with each pressure pulse. Garrett was shouting something, telling the stokers to bank the fires, but it was too late for that. The furnace tubes held too much heat. Even cutting the coal wouldn't drop the pressure fast enough. One of the rivet seams near the crown of the boiler began to weep. Not a leak, a seep. Water forcing its way between the plates, turning instantly to steam in the air. Then the plates themselves started to move. A bulge appeared on the side of the shell. Maybe an inch, maybe less, but growing. The metal groaning now, a deep, tortured sound that cut through every other noise in the mill. Drayton was already running, shouting at workers to get back, get out, move. Some listened. Others stood frozen, watching the impossible thing happening in front of them. The bulge grew to 3 inches, 4. And then the shell ruptured. Not all at once. It started as a split, a vertical crack that opened up along a rivet seam. Superheated steam screamed through the gap at the speed of sound, a white jet that could have cut a man in half. The crack spread, 6 inches, a foot, 2 feet. And then the entire section of plate tore free. What happens when a pressurized boiler fails is not an explosion in the chemical sense. It's a violent expansion. The water inside instantly flashes to steam, a 1,600-fold increase in volume, and that steam has to go somewhere. It went everywhere. The boiler shell split open like a seed pod. Pieces of iron plate, each weighing hundreds of pounds, launched through the air. One section went straight up, punched through the roof, and landed in the street 40 yards away. Another tumbled sideways, shearing through a support column and collapsing part of the second-floor gallery. The furnace tubes burst. Coal and burning metal scattered across the floor, igniting everything flammable. And the steam, God, the steam. 200-degree vapor filled the room in seconds. Visibility dropped to 0. You couldn't see, couldn't breathe. The heat-seared lungs, blistered skin, turned the air itself into a weapon. Thomas Drayton survived because he'd been running when it blew. The initial steam jet went over his head. He hit the ground, covered his face, and crawled toward where he remembered the door being. His hands found brick. He followed the wall, found the opening, pulled himself through. 14 other men made it out behind him. 7 didn't. When the steam finally cleared enough to see, the boiler was unrecognizable. The shell had peeled open like a flower, plates bent back on themselves, rivets scattered across the floor like rifle shells. The furnace tubes had buckled, twisted into shapes that shouldn't be possible. And in the silence after the screaming stopped, Thomas Drayton could still hear it. The faintest metallic ringing, coming from the wreckage. In 2004, a mechanical engineering professor named David Ashby was teaching a course on failure analysis at the University of Manchester when a student asked him about the Ashworth Mill disaster. Ashby had never heard of it. Most people haven't. It wasn't the biggest boiler explosion of the Victorian era, wasn't the deadliest. But something about the historical records caught his attention. Multiple witness statements describing unusual sounds in the days before the explosion. A boiler tender who'd kept detailed logs of auditory phenomena. References to vibrations, resonance, singing metal. Ashby got access to fragments of the original boiler. They'd been kept in storage by the insurance company that paid out the claim, then eventually donated to a museum that never displayed them. Pieces of corroded iron plate, still bearing the marks of rivets and the scars of catastrophic failure. He ran metallurgical tests, found exactly what he expected: microfractures riddling the metal near the rivet holes, stress patterns showing repeated thermal cycling, evidence of pressure far exceeding design limits. But then he did something else. He built a computer model. Using the dimensions from the original specifications, the material properties of 1870s wrought iron, and the pressure cycles documented in Drayton's log, Ashby created a finite element simulation of the Ashworth boiler. He ran it under the conditions Garrett had been operating it under. And the model sang. The simulation showed harmonic resonance at multiple frequencies, pressure waves synchronizing, shell plates vibrating at amplitudes high enough to produce audible sound. Even the breathing pattern matched, a low-frequency oscillation tied to the heating and cooling cycles of the furnace tubes. Ashby published his findings in the Journal of Failure Analysis and Prevention in 2006. The title, Acoustic Precursors to Catastrophic Pressure Vessel Failure, a case study from Victorian industrial England. His conclusion: the whispers were real. Not supernatural, not imagined, not mass hysteria. They were the sound of a machine destroying itself, broadcast through the metal for anyone willing to listen. Modern boiler design has come a long way. We use better materials, better welding techniques, sophisticated pressure relief systems, real-time monitoring with sensors that can detect vibration, temperature anomalies, even the acoustic signatures of developing cracks. But the lesson of the Ashworth boiler isn't really about engineering. It's about listening. Thomas Drayton heard the warning. He documented it. He reported it. And he was ignored, not because William Garrett was stupid or cruel, but because stopping the machine meant losing money, meant admitting a mistake, meant choosing safety over productivity. That calculation still happens today. Different industries, different machines, same human pressures. The fragments of the Ashworth boiler are currently on display at the Museum of Science and Industry in Manchester in a small case labelled Industrial Accidents, 1870s. Most visitors walk past without stopping. But if you do stop, if you look closely at the twisted metal, at the rivet holes stretched into ovals, at the fracture surfaces that caught the light wrong, you can almost hear it. That faint, metallic whispering. The sound of a machine that tried to warn us.